And today actually I'll be starting with a new topic called complex analysis. And this is actually short syllabus, very short syllabus. And the weightage also actually not very great like other topics. So somewhere around 50 marks actually will be there for this particular topic, right? So this complex analysis is actually one of the very easy syllabus, and the models also actually almost every time actually it will be repetitive in nature most of the times. And so this actually I will be covering some basic aspects like, so what is the syllabus? What is the syllabus? And the second one is, what are the books to follow? And then third one is, what is the weightage? Right. And the fourth one is, what are the important areas? Right. And approximately how many number of hours? Right. So these are all the basic aspects I will be covering, and if you wanted me to add any questions, I will add it to this. Right. So before proceeding, actually, I will just start with the syllabus. Right. I'll just write down the syllabus. So this is analytic function, Cauchy-Riemann equations, analytic function, Cauchy-Riemann equations, Cauchy-Riemann equations, Cauchy's theorem, Cauchy's integral formula, Cauchy's integral formula, power series representation of an analytic function, Taylor series, Taylor series, singularities, Lorentz series, Cauchy's singularities, Lorentz series, Cauchy's residue theorem. Cauchy's residue theorem, contour integration. Right. So this is the complete syllabus actually what we are going to discuss as part of this particular topic. So in this actually analytic function, so I will give you the brief idea of this particular syllabus. So in case of analytic function, actually we will try to check the complex functions for the differentiability. So if the function is differentiable for a complex function, then actually we can say that that particular function is an analytic function. But let me explain what is a complex function first, so that actually the entire thing actually is little different from the complex numbers. So this is a complex functions. As and when we have a number, then we can represent a variable as well. So we have only two different types of numbers. One is the real numbers, another is the complex numbers. So real numbers actually we have the real analysis, and the same thing as this one correspondence from the real analysis to complex analysis, because we have another variable, the complex variable, right? Now the fundamental aspect that we need to understand in case of the complex analysis is, we have actually in case of real analysis, so if xy coordinate system actually we have taken and given the function y is equal to f of x, so it assumes some particular shape like this, which is y is equal to f of x. Now here y, which is the output, is a single variable and it is a single valued function, and x is actually another independent variable. So this is the dependent variable, this is the independent variable, both are the real variables. So hence actually this actually sometimes even be represented as R2. So R2 meaning two different real numbers. So two different real numbers meaning horizontally you can represent the real numbers like 1, 2, 3, 4 like this actually, or 0.1, 0.2, 0.3, any number actually which we use in the normal number systems actually is the real numbers. Similarly, actually the y-axis also minus infinity to plus infinity, you can represent the numbers which are the real numbers again, and then actually we are correlating a real number to another real number with some kind of characteristic called as the function. So this is the function. Now the problem is actually in case of the complex numbers. So complex numbers actually it won't be like real numbers. Two real numbers together with a condition that one number is actually perpendicular to the other one, that one actually is called as the complex number. So this is, let us say this is x and this is y, then actually one single point actually this location is represented as x plus iy. So this single point actually is the x plus iy location. The meaning of it is from this origin, so along this actually with a length of x and the vertical direction with a length of y, these two together x plus iy. So x plus iy actually is together a single variable. So here x itself is the variable and x plus y iy together actually is a complex variable here. So that means if you are able to relate one independent variable and one dependent variable with two-dimensional analysis or the two-dimensional coordinate system, then actually if I define a function which is a function of x and y together, that is, suppose if I have f of z function where z is given by x plus iy, then f of z is equal to z square plus 2z. Let us say this is the function. Now z is a complex variable, it's not a real variable. Like this case, in case we have f of x is equal to x square plus 2x, and this actually we know how to draw in case of this two-dimensional system. But how can we represent this particular function? So this particular function on two-dimensional system, can we represent this? F of z is equal to z square plus 2z, where z is equal to x plus iy. Can we represent this number system? No. And if at all we wanted to represent, what is the dimension of the coordinate system? What should be the dimension of the coordinate system if we wanted to represent? So it will be a four-dimensional coordinate system actually we will have to think of. But actually, practically imagining a four-dimensional coordinate system is not possible. That is the reason actually what we do is we will try to have two different two-dimensional coordinate systems. So that is, this actually we call as the z plane. So usually actually this is called as the z plane, and another plane actually we will define, which is what we call as the w plane. So this is the w plane. So this w plane actually will have the real variable as u and the imaginary variable as v. Then actually we will be defining this function y. So w is equal to f of z. So let us say this is z square, or simply z square rather than this. So this is simply z square. Then actually f of x plus iy, and this is the z value, right? So this is x plus iy whole square. And then actually, so this is x square minus y square plus 2xy into I. Now this portion actually will not be involving any imaginary part, and this is actually purely the imaginary part. And this actually u of x comma y, and where v of x comma y is this one. So this can be practically u plus iv, where after the calculation for each point on this particular region, suppose actually you are talking about the region now. So here actually we call as the point, but here actually we always talk about the region. Why? Because on this line actually you can have any number of values and correspondingly you can calculate the value of y. But here this is one plane, this is another plane. For each point on this particular plane, there will be a corresponding points here, maybe one or maybe multiple points actually that can be there on the W plane. So that's why actually we talk about the multiple points within this particular region. So that's actually in the complex domain, we always talk about the region where the function is analytic. So that means the set of all the points where the function is analytic. So that is called as the region. For each and every point on this particular XY plane, so within this particular region, according to this particular function, you will be calculating these values, and then the u value will be taken here and the v value will be taken here, and then actually we will be noticing all such kind of correlation for all the points which are present in this particular region. So here actually it may be a circle like this, or actually it may be some random shape like this, or it can be any kind of shape actually, but there will be a correspondence between these two. So this is called as the Z plane and this is called as the W plane. So this is how actually the complex analysis actually we are going to be analyzing it. Now, as and when we have any number system actually with the variables actually we want to analyze, so the basic calculus actually is the analysis part. So the calculus is actually the continuity, differentiability, and so continuity, differentiability, and the existence of the derivative. All those things actually we will be checking. Like the case of the normal calculus, we will be extending for two different variables together. That is actually the complex variables actually we will take it. Like so the limit actually we will be talking about limit z tends to 0, f of z like this. Like the way actually we did it in this particular case, limit x tends to 0, f of x. So this value actually will be calculating the limits actually with some kind of process here. The similar kind of process actually we will be extending for this particular domain is called as the complex analysis or the complex variables. Got it? So then actually we will check whether the function is differentiable or not, or continuous or not, and then integrations, differentiations, everything actually we will do it in case of complex analysis. Got it? So the fundamental understanding is actually why do we will have to learn this complex analysis? So to answer that question, so there are a lot of advantages in case of the complex analysis to deal with certain kind of unsolvable integrations with the real analysis. That is the contour integrations actually it gives some kind of beautiful techniques so that actually you can easily solve the real analysis integrals in an easier method. Sorry, right? So that is one important aspect, and another important aspect is practically we will be using this complex analysis in case of the fluid dynamics. So in the fluid dynamics actually, so as I said earlier, complex analysis and the vector analysis together, it will be a single topic called the fluid dynamics. So this is the only part actually we will have to learn so that actually you can make it on the fluid dynamics very, very easy. Got it? So this is the one. Now actually, so with this basic understanding, if we analyze the syllabus, so analytic function meaning, so whatever the function actually, if the function complex function is differentiable within a particular region, then actually we call that function is analytic within that particular region. So analytic is a synonym for the existence of the derivative for the complex variables. Got it? And then Cauchy's Riemann equation. Cauchy-Riemann equation says, so that is, so to check whether the function is analytic or not, we will have to check the existence of the derivative, right? And here actually, Cauchy-Riemann equations actually, if you wanted to check the existence of the derivative, we have to be aware of the limits in case of the complex analysis. So the limits of the complex analysis to check actually, you have to make infinite possible variations, and each and every possible variation actually we will have to check whether the limit exists and that limit value is unique or not. Now in such case actually, it is impossible to check the infinite variations in case of the existence of the limit. Like actually in the case of the real variation, suppose a function is there like this. Now actually at this particular point you wanted to check whether the function is whether the function derivative exists or not, or the function limit exists at that particular point or not. Now here actually if it is a, then on the left side actually this is what we call as the a minus, on the right side actually we call this as the a plus. So a minus values and the a plus values actually we will check at this particular point, and at this particular point, if the limit value on the either side is actually equal, then we call that the limit exists. Now here actually we have only two different possibilities, either on the left side or on the right side. But in case of the complex analysis, what happens is this is x and this is y, and this value actually at single point actually we call this as the z. And at this particular z value, if you wanted to reach this, you can approach in this way, 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 you can approach in this way. So there are actually infinite number of possible variations that are there actually to approach that particular point. So all such kind of infinite paths actually you will have to check for the uniqueness of the limit value. And as it is impossible to check the infinite variations, what we do is we will check the bare minimum conditions. That is, at least actually, if you check along this particular path and along this particular path, one horizontal and one vertical, and then actually if you are able to prove that actually both are equal, then actually you can think of the further level. At least the bare minimum conditions is one path like this, one path like this. If you check it, if both are equal, then actually we can proceed further. Actually, as it is sufficient, actually in some cases actually we can conclude that actually the existence of the derivative or the existence of the limit at that particular point. So the bare minimum conditions with which you are able to finalize at least there is an existence of the limit is called as the Cauchy-Riemann equations. So you will have actually two conditions you are going to get it, which is what we call as the Cauchy-Riemann equations for the existence of the limit. Got it? So that actually we will be studying it here. And then actually Cauchy's integral formula. So this is the Cauchy's integral formula actually is the basis for the Cauchy's theorem. And this is actually how to find out the integrations for the complex functions. So like actually we have actually in the normal integrations actually we have f of x into dx. So this is actually the normal integration. In the similar way actually if we have f of z dz. Now can we do this kind of integration in case of the complex analysis? Yes, we can do that. And the interpretations actually we will do it in the real time, real analysis. So f of z dz actually will have implications even in the real analysis as well. That means there are some new advantages or new theorems actually we can use, or we can have actually another theorems what are not present in case of the real analysis. So in the real analysis actually we have certain integral theorems, right? Like actually so a to b f of x dx, and that actually if that is equal to f of a plus b minus x dx, then actually so that limits actually we can interchange it. Like this actually we have certain theorems in case of the normal real analysis, and along with those analysis there are some other new techniques actually which we can get it with the help of this Cauchy's theorem. So what it says is actually if the function is analytic, then actually without doing the integration actually we can conclude that the integral value is 0. Like this actually there are some techniques actually we are going to get it. That's what actually we call this as the Cauchy's integral theorem and Cauchy's integral formula, and the extension of that is actually the residue theorem. So there are actually 3 different integral theorems actually we are going to discuss it, and that will be part of this one. And then actually so a function actually generally in case of the real analysis actually we have the expansion. So that is the Taylor's expansion actually we have discussed earlier. So that is given a function actually which we can expand with the help of the Taylor's expansion. Can we do the similar kind of thing in a case of the complex analysis? So to answer that question actually there are 2 different possible variations. One is the Taylor series and another is the Laurent series. So Laurent series is possible only in the case of the complex analysis. In case of the real analysis actually we have only the Taylor series. Right, so that actually the similar one correspondence actually you can notice this here. So Taylor series and the Laurent series, and singularities actually that is actually the places actually where the function is not having the derivative, that is non-existence derivative positions are called as the singular points. So that actually it has some advantages actually or some kind of applications even in the complex analysis. So even in the fluid dynamics analysis actually we will use these singularities to identify some of the fundamental aspects of the fluid behavior, and that actually we will be discussing the singularities, and then actually the Cauchy's residue theorem, and the contour integration. So last one is the contour integration. So contour integrations also actually we will use these theorems, and we will assume certain contours to find out certain categories of the integrals. So if you people are from the electrical engineering background or electronics engineering background or the mechanical engineering background, you can notice that actually in case of the control systems actually there is a topic called the Nyquist plot or Nyquist criterion. So Nyquist criterion actually is just based on this contour integration technique. Got it? So there actually we will assume entire right side plane actually we will the entire right side plane, that is the infinite radius semicircle we will assume, and there actually we will prove that actually there are no poles present for the transfer function on the right side with the help of this contour integration or technique. Right, so that actually will give us a lot of advantages in finding the stability of the system. So like this actually we have some techniques, and some of the real integrations are the improper integrals actually which we will not be able to solve in the case of real analysis. The same thing actually we can use some kind of contours designed specifically to solve such kind of integrations, that actually we will learn in the case of the contour integration. So this is the complete syllabus and very short and simple syllabus. It won't take much time to discuss this entire topic, and usually actually I think somewhere around 10 to 15 hours actually we will finish this particular topic. Got it? Bilinear transformations, no, it's not part of our syllabus, right? Right? That's not part of our syllabus, bilinear transformations. right? So this is the complete syllabus. And any questions on the syllabus? Right? Any questions? Right. And the second one is actually what are the books to follow? I use only one book, BS Gravel. This is good enough. Right. If at all there is a need, then actually I will suggest. So Krishna series, I think there is one complex analysis book, and that actually, so a little advanced aspects of the residues actually that was discussed. Except for that fact, this book is good enough, BS Gravel. So it covers actually almost every aspect. If you wanted further practice, then you go for the Krishna series. But this actually needs to be solved first, right? And then what is the weightage of this particular topic? I think usually this is around 50 marks. And then actually what are the important areas of focus? So the questions actually that will be asked actually mostly from the Taylor's and the Lawrence series and the contour integration, right? And very rarely actually about the Cauchy-Riemann equations. So those are the two areas, the contour integrations and the Taylor series and Lorentz series. And there is one more area that is the residue theorem. So those are the three sections actually which you can use, which you can practice more so that you can get the full score from this particular topic. But actually, like every other topic, so whatever the areas actually I was explaining, like actually I say that contour integration, but actually without knowing the Cauchy's theorems, actually you will not be able to do the contour integration. So like this, actually, there are interdependencies. Though I mentioned some of the important areas, those areas you will be able to focus and solve only if you are good at all other aspects. Got it? So that's actually entire topic is important indirectly. Clear? Right? BS Gravel engineering book or separate reference book? BS Gravel higher engineering mathematics. Got it? Any other questions? Right? Approximately I will be taking this actually 10 to 15 hours, not more than that. Right? Within that actually most of the syllabus will be finished. Right? You tell me if you have any questions. Right? Okay. So that's all for today. So